Back for more sorting. I have finally got some free time again. It's been a few weeks. So where are we up to? Oh, I have to remind myself, and I probably have to remind you as well. So far, we've done a sort, which is like the quick sort style, splitting it only into two. Pivot has not been selected from the array. Instead, it's been cooked up like in a radix sort. The one piece of like smart sorting that's been done so far is that it's going through and checking to see if the radix that's being used for the split is going to be informative or not. But the cost of doing that is that we have to scan through the entire array, whereas a quicksort doesn't. It just does a quick little sampling. So that's where we are. Lots of room for improvement. In the previous video, I also had sim turning up, and I applied that to the reverse. If you discover the array is entirely reversed, it will sort of go and do it very quickly. That was pretty successful. Off camera, I did do simmed for the pivot selection as well. It makes a very minor improvement because most of it is in the sort of this computation, which it couldn't speed up, having to permute arrays and things. But that's where we are. Let's have a quick look at the performance of the code. Here we go. This is the profiler. So the partition, which is inlined, which is quite nice, is the most expensive part. That is where it actually walks through left to right, right to left, and does the swapping, the partitioning of the quicksort style sort. Then we have the base case, which is not far off, so it's fairly balanced between this insertion sort for the small arrays and the partitioning. Okay. Then we've got a scan of the arrays where it runs through 1.6 seconds, generates the pivot value. That's a bit expensive. It also detects whether it's reversible or in order, and so it can abort early, so we do get some benefit for doing that. And the one extra piece I've since added is another second being spent as a second pass through the array to find out exactly where the pivot is. Two useful parts for this. One I mentioned earlier where I thought we might be able to preserve the sortedness of the array. In fact, let me get a blackboard up. Okay, so you'll try and draw with a mouse. Here was the concept. You got an array, there's a pivot point, oh my god. There's a pivot point in the middle, and when we do the partitioning, you would normally scan from left to right on this side, and you start from right to left, and when they meet, you know you've discovered the pivot. You don't know where the pivot position is to begin with. And within that, some of the pieces, some of these elements that are out of order are going to be swapped with the elements that are out of order on the other side. On average, it's about half of them will be out of order in a randomly sorted array. And so what happens as you scan left to right, right to left, like this, the order gets swapped. So these ones, if they were in ascending order, if they were already sorted relative to one another, they'd become unsorted or descending order when they've been flipped to the other side because they're traversing in opposite directions. So my thought was, if you could detect whether this subset was sorted or not, you'd be able to choose which direction you traverse in. The only way you could ever traverse left to right is if you knew where the pivot position was to begin with. So that's one of the reasons I decided to put this in. We could do that. How much does it actually preserve? I don't think I'm going to do it today because if you think about it, okay, if these are both ascending, this sort of half the points that we're looking at are both ascending, then the traditional way of going inside out would cause those to reverse and you would corrupt it. So that's a bad case. But there are three other cases. There's there's also the case where, say, this is ascending and this is descending, and there's not much you can do about that. One of them will get corrected, the other will get ruined, and vice versa. So, you can't win. And then the fourth case of the four is where they're both descending, right? They're sort of out of order, and then, actually no, hang on, that's the case. When they're both out of order is the case where they will both get flipped from going the traditional way inside out. It will get corrected. We get the benefit from the case where both are in order, which is probably what I said first, in which case, by doing it as the arrows are shown at the bottom, you can preserve that. So that's, in one of the four cases, we can do better on half of the array. So it's like helping 1/8, which is not a great multiplier. I'm not too keen to test it out just yet. And even beyond that, if you use the traditional way, it's going to cause some problems. And then when it recurses and does it again, it's going to undo that because it's going to keep flipping things back and forward. And so it's going to recorrect some of the issues. it adds. And what's going to matter is at which point it hits the insertion sort case. Is it the one where it's improved things or where it's ruined things a bit? And I'm guessing that's 50-50 again, so it's probably something like a 1/16 or... it's hard to tell. It's not going to be a big improvement. Right, the other thing we should consider is the overall performance. So the current attempt is blue, and the next update, what we're just working on, is in red. It's slower. Why? Because I added that extra pass-through. We've got 2 passes through the array. But I have a plan. I have a plan for the second way of improving things. So again, we're going to see this throughout all of them. We have simmed implemented for both, so we're still very quick at reversing over here. We're still very quick at reversing. And that's the state of play. One thing I think I should do is add some more sorts. So now that we've got simmed in there, it's only fair to apply it to some other simmed sorting. So I'm going to add in 2 that have come from NumPy. There's the NumPy's quick sort, which has turned into a simmed implementation. I don't know how recently, maybe in the last year or so. And I've got their radix sort, which has been around for a lot longer. So let's chuck those in and see what happens. Okay, we've added them in. So red, remember, is the next update with the previous one. We've got orange being a simmed version of quicksort, which is actually not doing any better than the Golang PDQ sort. So that's interesting. And also the radix sort, where we're getting, that's got a very low constant. It is pretty quick. That's interesting. Next, we've got this sort of sawtooth, and both of the 2 from NumPy are doing a bit better. TimSort has this weird thing where it does well on one very large size. Okay. Over here, the simmed, this is for 20 unique values. Interestingly, the simmed quick sort is the fastest, a lot faster than its radix sort. So those simmed operations, there must be some trick there. It's doing quite well. It's a little bit we can gain. They have a really bad bit of overhead, so they're really slow on the 100 length arrays. Let's come back to this. I'm going to remove those. There we go. Now we can see what's actually happening. They're all a bit rubbish. This is reverse sorted. They're not good at spotting it. Right, and now we can see they're also, they're not brilliant. So there's nothing to worry about there. So the big case is the radix sort is just nailing it. And that does bring me to today's idea. I've gone and found the pivot position, and that's what's required to move from a quick sort to a sample or radix sort. We're going to an in-place version of it. If we know where the pivot positions are, then we can use an in-place buckets and make sure everything basically does that swapping from left to right across every bucket rather than across 2 partitions. So the new bit of code, we get the pivot location. That is fine. We're getting 1 pivot value. So what we want to change now, this is where it goes through and does bitwise ands and ors to find out which bit is usable for a pivot. We want to get 2 bits so that we can cook up 4 buckets, 3 pivot positions, including 0. So where do we actually get the pivot? Here it is. All right, so let's just make something called pivot 1. In N64, yep, pivot 2. If it comes through and we end up saying it's the 0th position, I think that's okay. It might have to be -1. So it does this once and returns it. That's 1 pivot. So instead we want to say, that's kind of right. Pivot 2 is now 1 lower, which is not correct. So now after we've got that first pivot, we can just repeat and get the second. How does that look? So this is going to be pivot 2. That'll be right. If it's hit 0, let's give it a pivot of 0. We're going to return 2 pivot values. Really should have thought about what I was doing beforehand, but... So those are our 3 pivots. We can cook them up like this. Pivot 1 is going to be the base OR with that. Right, that's the 1, 0 case. This becomes the 0, 1 case. Pick up. Question, why did you not pick that up? And then that becomes the 1, 1 case. And the number 0 is our other pivot. Cool. Okay, where is this called? Generate pivot value. Hold up. Okay, that's right. Generate pivot value. So pivot 1, 2, 3, 4. 1, 2, 3 sorted. How about if our pivot location finds the pivot locations for pivot 1, pivot 2, and pivot 3. Call them pivots, but they're no longer pivoting around them. They're going to be bins. I will change it some other time. So there's no longer a mid. They are going to be pause 1, pause 2, and pause 3. So let's change get pivot location. Need to return 3 ints, correct. Good God, what was I doing? We are counting the ones in between the different pivots. Yeah. Count how many are less than 1, how many are less than 2, how many are less than 3. That will give us the correct spots. Yep. So I'm doing this without an if statement, which I think is the right thing to do. Don't know if it's going to read from the slice each time. Will it be smart? I don't know, just in case. Yeah, thanks. Makes me feel better. So this is incorrect because it's not the entire... Oh, no, it is the entire amount. That's the positions. Well done. Okay, let's generate pivot location. Wait, what? We need the pivot position with the pivot value. Do we need the pivot value? Once you know the pivot position, yeah, we do. 1, pivot 2, pivot 3, pause 1, pause 2, pause 3. I mean, you could put it in a separate slice and then we could do more and more bins, but if we can keep them in registers as variables, that will be quicker. So we're just going to divide this into 4 bins only. We're not going to do 8 or more. Let's try and do this as quick as I can. Again, lunch break, time limit. All right, we'll stop doing this. Let's just work directly from the input slice. I1 is 0. This is the current place we are sorting in the first bin. I2 is going to be pivot pause 3, pause 1, sorry. Yeah, no, 2. 3 goes to 2. 4 goes to 3. Well done. Now we continually sort. Yeah, okay. It walks up the first bin, so we are going to... Walks up the first bin, stops, walks up the second bin. Yeah, we're going to change this. So we're going to walk up every bin until we find one that's out of place. It's less than pivot 1. Correct. It is less than pivot 2. Incorrect. It could be anywhere that's not in the bin. Data R2 is greater than or equal to pivot 1. So I'm saying the pivot values belong in the next bin up. Must remember. Why are there only 3? There should be 4 bins worth here. I4 is less than the full length, and it is... I don't know why you need to be in parentheses, but fine. It is greater than or equal to pivot 3. Yes. Probably knows what I'm doing now. So if I1 is greater than or equal to pivot 1, and I2, so forth and so on. Actually, we shouldn't do this every single time because it's a lot of additional checks, 4 of them. So we should do that once, get them all in the right position. Then we're going to pull one out. And we would probably do it from the first bin. We would place it in the bin it belongs to, and then, which is like a swap. And then shift those 2 forward. Is that right? No. Right, what's our current values? So we're going to have to keep the current value in memory. It's not, okay, we'll call this index 1 and index 2. These are the places that we're working from. So we'll do this forever, until we no longer have bins to work on. No. Stop it, AI. You don't know what you're doing. So what we're going to do, we have an index, we want to see where it belongs. If index 1 is greater than or equal to... So we need v1 and v2. v1 is equal to index 1. No. God, it clearly doesn't know what's going on. So I suppose I haven't been telling it. Now, if v1 is less than pivot pos than pivot 1, then it belongs in the first bin. So we swap it in. That is right. And v1 is now equal to v. I think we could have done that in one line, but this is okay. Then we need to shuffle forward, and that'll be this one here. So that bin moves forward to its next value. Like, dudes, seriously. Now, at the end of that, we are actually done, so we should continue. And we have to repeat this. Hold up, so we don't even need v2. Really? We got one that's out of place, and we swap it into memory, and we just continue. Yeah, that seems right. If v is less than pivot 2, stuff. 3, stuff. Otherwise, it has to go into the 4th bucket. Stuff. No. Buckets may have finished. 4 done. It's going to be I1 is greater than equal to pivot pos 1. Thank you. Good. If they're all done, break. Nice. Okay, that seems all right. Verbose, but it should work. That's partition, but then we have to do the recursive call 4 times. Where is partition? There. Okay. I think I may have bitten off more than I can chew for a lunch break. So let's test the pivots. Starts at 63 and starts ticking down. We make a pivot 1. We then, let's clear that out. We didn't break. Okay. Right, now the pivot positions are at 2, 2, 2. 12 to 12, they're all the same. So I has not been decremented enough. Goes down. I was a particular value, it breaks. We try I again and it's fine. So I minus minus. Okay, now we've got 2, 1, and 3, so we're giving them back in the wrong order. Let's go through this. 1 is the middle one. That's pivot 2. And then this will be the lowest one. And then we combine the 2 to make pivot 3. What have we got now? could actually just catch the case with only one pivot value and do the regular sort, have two functions. Believes 1, 7, 10 versus 6, 7, 10. This could be important for get pivot location of these ones. So 8, it's over here. So it should be this one, 0, 1, 2, 3, 4, 5, 6. Position 6. Oh yeah, it was right. Right, let's do a quick test here. Yeah, that passes. Be where we partition. No, where we call the partition recursively. I was doing those recursive calls for the quicksort ints. 1 to 2, 2 to 3, 3 to up. Because some of them are, yeah, repeated. And then we always have to shrink it. Not sure if that's really the problem we've hit. We need to do some kind of test. Yeah, what are we doing here? Still got issues. Oh, this is sad. Okay, I'm going to have to stop this and I will pop back and record after I've just done the debug. This a bit unfortunate. Can't do it in one sitting. Okay, a bit of a marathon. Till next time. I'm back, round 2. This is just the end of the work day. I realized what mistake I was making. In the sort, I was going through, pulling one item out, finding the bin it goes in, pulling one out to the next bin, and so on. That works until you hit a cycle. So normally with a quick sort, you pick one up, you sort it with another, and it's done. And you've cycled from one to there and there back again. In this case, with multiple bins, we don't know how long it's going to take. It might keep hopping around through the bins, but it will never be more than 4, I guess. You will always return. You have to return to the bin you started at. And then the value that we first got up here, this v equals the index one, is going to be wrong. Because it will already have been written somewhere else, so you don't want to pull it out again. But what we've got to do is take this piece here that chooses the next useful index. Yep, it's going to pull one out. Okay, look, I just want to tab. Because I could have do it. That's wrong. What? No, guys. No, don't change it to I3. That was no. No. V is data I. Not colon equals, just equals. Otherwise it's equal to I2 if it's larger. Good enough. Okay, so it's not failing. Let's just double its size. Okay, look, we hit a problem. Come on. Cannot reproduce bug. Off the cuff, I don't think that's any quicker. Partition is really slow now, as it should be. get pivot location, yes, these scans happen much less often. And get pivot value, even less. So that makes sense. Partition, super slow. The big ones. The usual place where we're scanning forward. Break, if we're back at the start V, do some stuff. But yeah, does that add up? There's 1 second, 2, yeah, 3, 4, yeah, I can see it. It's all in here. Bang. No benefit. All right, I'm going to stop here because this has not been a successful run. Hopefully we get some better improvements next time. Cheerio.